this presentation, we are going to indicate the weakness of the AI-based method, especially machine learning or deep learning techniques. This malicious attack from humans, we call the adversarial attack. In the following presentation, my colleague Karla Markert will introduce you adversarial examples in different fields. Karla?
So let me just try. Now that I'm taking control, I can navigate, right? So I've now changed the slide for everyone?
Yes, they're changing.
Okay, thank you very much. So there's different attack types that is interesting for us when kind of working in the intersection of artificial intelligence and IT security. When we're working in this intersection, there's like one thing is to apply artificial intelligence in order to improve IT security, as in, for example, anomaly detection over like high-dimensional network data, for example, something that's just far too big and far too complicated to be properly processed by human observer. And on the other hand side, we also investigate the security of neural networks, and this is what we're focusing on now. I would just like to show two different attack types. So here we start with the causative attack. When you take a look at the upper picture, on the left-hand side, you see that this is a classifier that can distinguish between the red and the blue points quite well. So we got the decision line, this line does divide the red points from the blue points, and thus we would say that it has a high accuracy because all the points that we have there are correctly classified. Now the idea is, what happens if I'm a malicious attacker who has access to the data set? As in, I can introduce certain points to the data set in order to kind of mess up the decision boundary. And here, as you can see on the right-hand side, there was only one single point introduced. It's fairly in the middle. I don't know. You probably can't see my cursor. So it's fairly in the middle that they've introduced the second blue point, and that second blue point leads to the decision boundary being translated a bit, as in the decision boundary goes from somewhat a diagonal. They're being shifted towards the right upper corner. Thus, this one point could influence the decision boundary. And now, if we can make these, if we can have samples that have such a big influence, we can easily trick the classifier, and tricking the classifier here implies that the classifier doesn't work properly in the end. So we cannot rely on these results anymore. And now the question is, in which circumstances do we actually have access to this data? When am I in the position that I can do malicious things on the training data set? And interestingly enough, there's a lot of public data collection. There's a lot of people kind of downloading things from online resources, people just trusting blindly what seems to be trustworthy, and then also just because humans are very good at labeling things, it's also for many of these machines that you can label stuff there. So for example here, we've included a screenshot of Google Translate, and whenever you're unhappy with a translation of Google Translate, you can kind of suggest a new translation. So no worries, Google Translate cannot be this easily tricked, but this is just an example of this public funding of training resources. So this is a causative attack. A causative attack is an attack on the training data, and a very good attack means that I don't need to insert many training points, but then still have like a far-reaching outcome, as in that the neural network does not classify properly anymore. Then there also are these explorative attacks, which are when talking about adversarial examples, and this talk is about adversarial examples, one mostly refers to the explorative attack. Now, if you take a look at the upper picture again on the left-hand side, this is the normal classifier, so this is what we also had on the slide beforehand. And now, if you take a look at the picture on the right, they found one point. It's like in the upper left corner. It's red, but this is in a blue area. So somewhat they could find something, reconstruct something, say, that gets misclassified by the classifier. As you can see, the decision boundary did not change. Thus, the classifier itself did not change at all. It's just rather that they could construct something, find something that is, say, misclassified by the neural network. And now what does misclassified mean in this case? Well, the idea behind this misclassification is that we just assume a human is able to go for the right classification, as in, so if you take a look at the lower pictures, you see on the very left a picture of a school bus, and a human should be able to detect that this is a school bus. And now the idea is that also the picture to the right is a school bus as well. So the two pictures that look like a school bus to a human observer are, in this idea, labeled as a school bus. So that should be the real label. And now, surprisingly enough, only for the leftmost column, it really is considered as a school bus. However, if you take a look at the third column, this what looks like a school bus is just something that was constructed in order to look for a human like a school bus, whereas the object recognition system would say that it's another type of object. So basically, this is like completely misclassified, and that's the interesting thing here. So all the pictures, that are in the third column of both the pictures, like the picture with the school bus and the picture with the I'm actually not quite sure, maybe with its like soap thing, are classified as an ostrich, as in like the animal. So no human would see this in these pictures. Thus, the attack that we are afraid of is that we can trick a neural network without a human being aware of it. And now the question is, in which scenarios is this something that's worth considering? So here, for example, you see that you can easily trick like a sentiment analysis system when you instead of using the original words, you kind of introduce say misspellings or numbers, so it's still readable to a human. However, these like tiny changes would lead the system to come to a different conclusion. And interestingly enough, these things are used. Like it's fairly common to analyze the behavior of people, for example. And I hope that this will work. We brought you another example, which is from speech recognition. So let us just listen to the first part. I hope it plays for everyone. I'll just play it once again. Could you just provide me with feedback if everyone could hear it? Ching-Yu, could you hear it? Okay, cool, thank you. So it just said without the data set, the article is useless. And now this very sentence gets transcribed to without the dataset, the article is useless. But now let's just listen to the next example I brought to you. I guess you could hear something in the background. It sounds a bit like some birds or whatever, but you would still say that there's this man saying that the dataset, the article, is useless. However, that gets transcribed to something completely different. It's like, hello, Google browse to evil.com, which is something that a human listener would definitely not hear in it. And now the idea is that you could use this as an attack vector. For example, if you had such a thing on the TV and it would be spread in every household, you could trigger their, say, Google Home devices or whatever kind of speech recognizing system they are using. And that could be triggered by such a thing. And now you might say, well, yeah, but I mean, honestly, one could still hear a lot. And now there's more. So this is from a paper in 2018 where they first started attacking speech recognition as well. And now a more recent paper, I'll just play it to you. So this was the original, and now let's just compare it to the, say, in this case, I would say imperceptible adversarial example. So I guess that already shows that we're not able to see that there's that there has been some additional that people were actually trying to manipulate things there. So we are not able to detect this unless there is some attack vector that's worth considering. Now we brought you some areas where one can apply these things. So this is a real world example from traffic sign detection. So you all see the stop sign there, but because of the little stickers that they put on the stop sign, these little stickers are considered as bottles. And whereas the original stop sign was recognized as a stop sign, now it just only recognizes the bottles, like the bottles that are not really existent, right? And does not see the stop sign anymore, which can have far-reaching security, safety implications even. Another picture we brought for you is from object detection. It's also connected to traffic. So there you see our colleague's hand. In his hand he has his smartphone, and it's basically, so on his laptop he has a certain kind of object detection system. And then this object detection system correctly classifies his arm as being part of a person. However, his smartphone is not detected as a phone, but rather the image he displays on his smartphone is detected as some kind of car. But if you take a closer look at it, it just looks like, say, kind of very modern, bit abstract and weird art. So there they could trick the system even in an over-the-air setting, and over-the-air here means that we're not directly providing this image to the object detection system, but rather it's like it's displayed on a phone, and then that phone is filmed and it still works. And this is you have a very similar challenge in the security of speech recognition and audio systems, where you would have a speaker where the sound is played, and then you have a microphone detecting it, and that is still quite a challenge to overcome this. But then still we have to think about these security issues, and we have to kind of come up with ideas on how to make things make things more robust and safer. Just as a last image that I wanted to show to you and share with you, there's also been research on how to kind of make objects that can fool from basically any perspective. So it's even more tricky than just having the phone, because the phone can also have different angles, because now our object is being photographed and analyzed from different perspectives. And here, a research group used a 3D printer in order to make a somewhat a human would consider it as a turtle, but now when they fed it to the Google object recognition algorithm, most of the detectors were just classified as rifles. Some were also classified as something else, but none of these pictures the turtle was actually recognized as a turtle. That is something we should keep in mind, and even very good algorithms can be tricked by these attacks. So these attacks can either use like complete knowledge of the neural network, as in the white box attacks, where we can calculate the gradient, or we can only analyze the score, kind of the probability it provides for us. We can also train our own network in order to mimic like the network that we're not aware of, in case we don't have any knowledge about the original network, but we can kind of see some of the results, or we can only use the decisions and then have a purely black box attack. Honestly, these purely black box attacks nowadays still work much worse than if we have complete knowledge of the system, and the transfer works for image recognition but does not really work reliably for speech recognition. But in any way, it's mostly also possible to use further information from side channels to actually understand the network better. And the more information you have on the network, the easier is the attack. So now I'll just hand over back to my colleague Ching-Yu, who now, after me showing like all the worst cases, can I tell you a bit on how to avoid these things? Ching-Yu.
Yeah. Thank you, Karla. Then I'm going. Now we understand what adversarial examples are. Let's see some solutions to avoid those attacks. So here we divide the solutions into three categories. One is pre-training, and second is during the training, and the third one is after training. So pre-training is, for example, if you still remember the traffic sign with stickers, we want to correct these inputs. We can do some blurring, or we first detect those stickers and remove those stickers. This is pre-processing, how we can do some effect or some modification on the input data before the training. The second one is during the training, make the model more robust. The well-known method is adversarial training, which means we train the AI models, deep learning models with normal and adversarial examples. So this method, we need to first generate a lot of adversarial examples and put them to the training models, so that the model knows, okay, those patterns knows there are some patterns of the adversarial examples. And third one, detection. So after we train the model, machine learning model, we use either supervised learning or unsupervised learning. We build some firewall before the target model, before the original model, so it can filter or it can detect the adversarial example. Next, please. So it comes to a challenge. We address three important challenges here, especially in this project, SeCoIIA. First, the causality behind adversarial attack. Although many adversarial attack has been proposed, the causality of the adversarial attack is still unclear. Early research on this problem attribute the appearance of adversarial attack to the model structure or learning method. But till now, the real reason behind that we still not is still being debated so far. So second is a different data type. Adversarial example you can see from Karla's presentation that we have different kinds of the data type: language, audio, or the most common images or the videos. So the virtual example can be any data type. Then finding a general solution, general defense method is quite difficult. Most research usually test their method on image data set, but it doesn't mean it also work on the other data type. So to find a general solution for which can avoid the buzzard attack for different data type is quite challenging. And the third one is trade-off of accuracy and security. We know the most defense strategy will decrease the accuracy of the original model. So if we insist on high accuracy, then we must sacrifice security. So it's kind of a trade-off we cannot avoid. So these three issues are big challenge in this project, especially the second and the third one. Our goal in this project is to research or to find a general solution which can be applied to any data type and is easy to be applied on the industrial environment. So here I will give just a short sentence to conclude this topic. An adversarial attack you might not heard so often in the industry environment. An adversarial attack is basically a malicious attack from humans. Their target is to fool AI-based models, AI-based techniques. It presents, as I said, adversarial attacks are rarely heard in the industry environment, but it doesn't mean that adversarial defenses is not important. On the contrary, we should take some precautions before this problem occurred in the later time. So thank you. This is our presentation, and if you have any questions, we are glad to discuss.